Hi everyone, I've got another example here of, it's got several things in it, but I would say the big thing is sketching antiderivatives and using the first fundamental theorem to be a little more accurate. So this one is fantastic practice. This would definitely be something I'd have students work on either alone or in groups during class. This would not be something I would just do. So please pause, see if you can work through this, and then come back and watch anything you get stuck on. Okay, so I'm looking at a graph of little f, and my very first question is to find the value of the integral, the definite integral of little f from 0 to 3. So that's saying that this is x. I want my interval to be here, and the integral is asking for area. So I'm looking for the shaded area there. And since it's piecewise linear, I would say we should just probably count boxes. Each box here is 10 by 1. So this is 10, 20, 30, 40, 55. So the area is 55. Include units in an illustration. So illustration is what I showed, shaded. I didn't really give you units, but we could say this is unit squared. Okay. Part B wants us to assume that big G is an antiderivative of this function that we're looking at. And we're also given that big G goes through the point 0, -5. We are supposed to use that to find big G of 3. So what I would say here is this is just asking you to very directly use the first fundamental theorem. So I would say that we know that the integral of f of x from 0 to 3 should equal any antiderivative evaluated at 3 and then 0. So let's go ahead and make it G. G of 0. And again, the reason it's any antiderivative is because if the C's are different on big G and on big F, it won't matter, because when we subtract, we'll get whatever that constant is minus that exact same constant. It drops out. So take your pick. Any antiderivative works for that first fundamental theorem. We're looking for G of 3. That's what we want to know. We were given G of 0. It's a -5. We also just figured out that the integral from 0 to 3 of f of x is 55. So we actually know that 55 is equal to G of 3, and then it's minus a negative, so plus 5, which means G of 3 should be 50. You can also think about this graphically. It boils down to the exact same thing, but you could say, okay, I'm thinking about this G of x function. It goes through 0, -5. I know that the integral of its derivative should tell me the change in its y. So if I do the integral from 0 to 3 and I get 55, that means that if I go over 3, my y value should increase by 55. So from -5 up 55, we would get 50. So same idea. If you like the visual better, go for it. Okay, so now we're going to look at a different antiderivative. I know it's an antiderivative because right here I'm told that its derivative is little f. So big F is another antiderivative of little f. I know it's not the same one because it has a different y-intercept. And we would like to go through and fill in the table. I have no idea why my x's became b's, but it doesn't make any difference to our answer. It doesn't make us wrong, so we'll just go for it. We know that if we plug in 0, we get out 10. Okay, so let's see. I'm going to actually go back and let's do a different color. I don't really feel like red. Let's pick this green that I like. Okay, so back up to the original graph. Okay, so we know that we start 0, 10. We know that the area under this curve is going to equal the change in y. So from 0 to 1, I get area 1 by 20, which is 20. Which means the antiderivative should increase by 20, and I almost wrote 20 down, but it's not, it's 30. So it was 10, goes up by 20, we're now at 30. If I want to figure out the y value when x equals 2, I could go back and start from scratch and say, okay, it was 10, how much area do I catch? Add that on. You can also just add on to what you've already done, as long as you're being really careful, otherwise your mistake will just carry through the whole thing. So if I know that the y value, if I know that f of 1 is 30, and I know that the derivative picks up area of 20 when I go from 1 to 2, that means my y value needs to go up by another 20 to 50. I don't know if I said that in a really rambly way, but we'll do more, so hopefully it'll make sense. Okay, so from 2 to 3, again, you have the same choice. You could go back and use your y-intercept, 0, 10, and you could say how much area do I catch between 0 and 3, and actually we've done that, so that's not a bad idea. But we could also try the new way and say, but I have another point. I know I go through the point 250, so from 2 to 3, if I pick up area 15, that means I would need to add 15 to my y value of 50, and I would get 65. So notice you would have done the same, gotten the same value if you went 10 plus 55, but instead we went 50 plus 15. So you can do this one chunk at a time, or you can go all the way back and start from the beginning and count up the whole area. Okay, from 3 to 4, I gain 5, so this should be 70. From 4 to 5, I gain another 5, so this should be 75. From 5 to 6, I gain 10, so this should be 85. And again, keep reminding yourself it's easy to go on autopilot, but the big thing that we're saying here is that the change in the y value of the antiderivative is equal to the area trapped under the derivative on the same interval. Okay, from 6 to 7, I catch another 10. So that should go up to 95. From 7 to 8, I catch 5, so I've hit 100. And now I'm actually going to start decreasing. So this is an area of 5, but the integral will be negative, which means my y value is actually going to, my y value on big F is going to decrease by 5. And then from 9 to 10, I catch... all this is 15, area 15. Again, it's below the axis, so I actually have to subtract that off. So it's going to bring my y value all the way back down to 80. So the first fundamental theorem, and in fact it's convenient to rearrange it, you could say if you're trying to calculate g of b, that you could get that, or here we'll say f since that's what we were just working on. So if you're trying to calculate big F of b, I don't like that B. Let's do X. That was nonsense here. Let's change it here as well. Okay. You would take the integral from, oh, now I see why I did it. Here, f of b is equal to the integral from a to b of little f of x dx plus f of a. So that's just taking the first fundamental theorem that says the integral is equal to f of b minus f of a and adding f of a over to the other side. So that's why I put this nonsense b in here, and then I forgot what I was thinking. Okay. D asks us to walk through some of the details that we did in the last problem where we decide when the antiderivative is going to be increasing, decreasing, concave up, concave down. So big F will be increasing when its derivative is positive, and its derivative is little f. So when little f is greater than 0, we're thinking y's, big F is increasing. So little f is actually greater than 0 for a decent stretch of this. All through here, we have to leave out 4, but then all through here as well. So I would say that little f is positive from 0 to 4 and then from 4 to 8, which means big F will be increasing on those exact same intervals. So 0 to 4, we need to leave out 4 because it's not actually increasing right at that point. It's flat. And then from 4 to 8, and the same thing with 8, little f is 0 when x equals 8, so big F will not be increasing at that point. The decreasing is going to be this stretch over here. So big F is decreasing when little f is negative, when the y values of little f are negative, which means from 8, I don't know, did I say? Let's just assume that the graph dead ends at 8, so we'll just say 8 to 11. 11 does not have to get a round bracket. The y value of little f is definitely negative, so big F should still definitely be decreasing. But again, there is some sort of weird things for dead ending and talking about slopes at an endpoint, so I would just say I wouldn't be super picky about that one. And then big F is constant when its derivative is 0. So constant means it's got like a horizontal tangent, or it is actually a horizontal line. So for this one, it only happens at individual points. Little f is 0 when x equals 4 or 8. But not anywhere else. So there'll just be a horizontal tangent line at each of those points, and there's nowhere else that we would say the function is constant. Okay, so concave up, concave down. Let me see if I can snag a color. This is actually questions about f double prime. So back up on the graph, remember that this is the graph of f. So if we want to summarize, big F double prime, which is actually little f prime. Let's see if I cannot mix you up. So right now what we're working on is we have a big F, that's our antiderivative. We have a little f, that's our function. We have a little f prime, that's the derivative of our function that we started with. But if we're trying to talk about big F, you've got to remember that this is the derivative, the first derivative, and this is the second derivative. So this really is a concavity question, means we need to refer to the graph of f prime, which I don't have, but I can get a lot of information about it. So what I know is that f prime is going to describe the slopes of this graph I have up at the top. So here, f prime is 0. Through here, f prime is negative. I have negative slopes. Interestingly, it's undefined right at the corner. Through here, the f prime is positive because f is increasing. And then we go back to 0. And then we're negative for the entire rest of this. So whenever f prime is positive, big F will be concave up. And that was only for a little stretch. That was only from 4 to 5. Whenever big F is negative, too many F's floating around. Whenever f prime is negative, big F will be concave down. So that's going to be from 2 to 4. And then from 7 to 11. And again, this is my bad. I need to go through someday and fix these. I've snagged graphs from people, and some people are bad about putting arrows or closed dots. Really, we should have one or the other so we know if the graph just dead ends there or if it continues to be a straight line forever. And then the last question is, when will big F behave like a linear function? And basically what that's saying is there's no bend. So the second derivative of big F needs to be 0, which means f prime needs to be 0. So from 0 to 2, that is true. And from 5 to 7. So the slope is not changing, which means, what do I want to say? Yeah, the slope is not changing on those intervals, which means the derivative will be 0. And then when we take a step back and say, okay, when this thing is 0, that's talking about the concavity of big F. So we got that from little f, but it's really concavity of big F. So big F does not have any bend on those two intervals. Okay, so lots going on in this one. The last part is to try and put this all together by sketching big F. So we know that big F goes through 0, 10, 130, 250, 365, 470, 575, 685, 795, 100, and then back down to 95, and then back down to 80. And we could actually do another point. I don't ask for it in that table, but you can see that in this last little section, our y value should drop by 1025. So 1025, that would put me, where'd I go, 80, 60, 55. Why does that look funny? I don't know if I counted wrong. Somewhere I did. Right here. Okay, sorry, that one was at 70. Now it's at 80. So now if I go down 10, 25, that looks a little bit better. Okay, so we have a lot of dots to connect. We also want to think about what we just said in part D. So we know that from 0 to 4, and then from 4 to 8, the function is increasing. There's a horizontal tangent right at 4 is all that's happening. So we get a little flat spot there. We also know that from 0 to 2, the graph is going to look like a perfectly straight line. It's going to be a perfectly straight line. So that's this part. So here, check, we got that. From 2 to 4, we know that it's concave down. So it's going to be slightly tricky to show. But from 2 to 4, this all has bend. Downward bend. Okay. At 4, we know we have our flat spot. From 4 to 8 is all back to increasing, so let's look at concavity. We know that from 4 to 5, we should have an upward bend. So there's my little bit of curve. And then from 5 to 7, it should look like a straight line again. And then concave down. Okay, so we're going to be concave down from here on. So we're going to be concave down, increasing. And then at, where are we at? At 8, we switch to decreasing. So from here on out, we're going to have a downward bend. Makes my max look a little crooked. And we're going to be decreasing. So that's a pretty decent sketch of F. It's a little hard to perfectly see the bend, but we talked through it, so hopefully that makes sense. And then the very last question here is, we had defined the function g earlier as well. We said it was another antiderivative, and I just want to think about how that graph compares to the graph of F. And the answer is that it has the exact same shape, but it has a different y-intercept. So F went through 0, 10. G should go through 0, negative 5. So it would start just below the axis. Otherwise, it would be identical. Let's see if I can get this right. 1.5. It's flat. And then it gets concave up. Sort of. I didn't actually ask to sketch it, but I'm going to for good measure. And then here and here. Okay, so that's a rough sketch. This is G. And the first one was... Okay, so two different antiderivatives should have the exact same shape and differ only by that vertical shift. All right, thanks for watching.